Because one of the places I wanted to start with this is considering, those kind of back of the schoolroom kids like me who, tolerably smart, but we're not proper propeller heads. We're not the mathletes of our schools. Um, you know, Dealing with this machine learning stuff, having a look around online, there are loads and loads of videos, loads of tutorials and things. Half of them seem to be a bunch of people that have imported the MNIST data sets, copied a couple of examples from somebody else's website, hit compile, run them, got a result, bam, they've got a video out there. There's no explanation of what any of this stuff does. And in terms of following it, they talk about tensors and weighting and activation and all the rest of it. If you don't know what any of those terms mean, all of this is just impossible to follow. I don't know what half of that stuff means, so now's a good time for us to explore it. There's plenty of learning materials out there. It might be slow, it might be clunky, it's going to take me a few tries to get stuff to work. I'm not even a very good Python programmer. Let's have a look, let's see what we can do. Let's start off with importing Numpy and TensorFlow. Um, Excuse me while I'm drinking my coffee as I do this. Numpy gives you a bunch of array and mathematical operations, mostly to do with array stuff, linear algebra, and transformations. It's commonly used in machine learning and computer vision applications. Really, you wouldn't be surprised to see that in nearly all of them. TensorFlow we tested in the last video. We made sure that works. If we just did something dead simple now, like tried to do print, we're using Visual Studio Code. The IntelliSense, the auto completion and stuff in this is just brilliant. It's really good. I would thoroughly recommend it. I'm not a big fan of Microsoft products generally, but this is, it's good. It's properly good. This is going to take me some doing because it's been a while since I've done much Python. Looks like C Sharp's string format, but slightly different. And I spend most of my time in the C Sharp world, so you'll probably see mistakes that look a lot like C Sharp. So let's do tf dot version. See what we got here. Save F5 to debug. Make sure everything works. There we go. For some reason with the virtual environments, I see these weird errors underneath things. Generally speaking, I haven't really been able to work out. Oh, that's interesting. That's not how that works at all. There you go. Maybe it's something like this. Hit compile. Nope. Um, well, that's got me slightly buggered. Let's have a look online and do a Python string format. You'd think I'd have known all this stuff before we got started, wouldn't you? What kind of professional video is this? Python string format. Sorry, it's off screen because I don't have a whole bunch of. Okie dokie. So I've got my formats confused. Okay, so let's do what I was doing before. %I, and this time it's .format, and now our value. What's it? TF dot version. Let's try that. Save. Oh my! I'm hopeless. Forgive me for this. This is even less. Okay. So I had a hybrid of the correct approach just by guessing. You can really tell I don't use a whole lot of Python, can't you? So close. There we go. All right. So the point of all of that is that our DL4CV virtual environment is running. We have TensorFlow and Numpy and all of those things there. One of the things that I mentioned just before was that Numpy allows you to do lots of manipulations of arrays and things like that. So let's take a quick stab at creating some constants, the equivalent of like a global variable, but a TensorFlow constant. Let's say a equals tf.constant, and let's put the value of 4 in there. B tf.constant 4 and 6. All right, let's have a go at, say, print. I reckon we can do this correctly this time. Dot format a value of a is cent I. I assume there's a toString of a TensorFlow constant that comes out as a 4 here. Oh, sorry, I did it again. Oh, well, really not good, huh? So we hit F5, we should get, okay, a value of 4. All right, so if we make a, yeah, we've got a second one. Let's do something else like, let's multiply them together. I'm imagining we can do equals A times B, print D equals, not falling for this again, stupid like a fox, huh? Let's say that was D. Let's dump that out to the console, have a look. Do we get what we would expect? A is 4, we get D is not defined. Oh, sorry, C. As the person watching, this must be infuriating. My apologies. I told you it wasn't going to be good. Okay, so we can multiply our constants together like that. That makes sense, I suppose. Let's try making something that's a little bit better for our application. We want to make a set of tuples, for example. I don't really know how to explain a tuple, to be honest. It's like an array of arrays, like a two-dimensional array. If you had a database table, each row in the database table would be a tuple, for example, where you might have multiple values. And again, sorry for sipping my coffee, but I have to. And by have to, I mean want to. Okay, let's make a tuple of some description. It's going to be 2 dimensions. And I believe, oh, that's right, we have to, it's an array of arrays in effect. I always get confused with Python with lists and dict and arrays and the different data structures. Again, being a C# kind of person, I'm guessing that's why they're ever so slightly different. So dtype dot let's say these are float 32s. Sure, that's how you do this. And of course, what do I need for a dtype? Do you think? I'm going to have to pause the video and work out how to get a dtype. Give me one sec. That was particularly silly of me. I had a typo there. That was really, really obvious, wasn't it? NP for NumPy data type. Of course, the data type is a float 32. That's better. No more errors. Always a big fan of the no more errors. Okay, because these are floats, we're going to put a decimal place with nothing much in it. So 2.0, 1.0. And let's say 1.0, 0.0. Actually, make that 0.1. Okay, so that's going to be our tuple. It's a tensor looks like this tuple, this shape. So let's make a second one and call it B. So he's multiplying these out. So one of the things that let's make that 3, 1.5, 1.5. 1.3 and 0.8. I don't know, just making these numbers up. So one of the ideas that you come across in this that you see a lot of in digital signal processing and computer vision and things is this idea of like matrix multiplication, things that are used for applying kernels in convolution to numbers. Convolution, from what I recall, is effectively multiplying everything in the first set by everything in the second set sequentially. Um, it's almost, it helps to think of it as like a recursive operation of multiplication. It's often used, yeah, like I say, in digital signals processing. In a lot of ways, that's the easiest space to understand it in because we don't have to worry about multiple channels to do with, say, colors, red, green, blue, and an alpha channel when you're doing vision-related stuff. It's easier to think of it as sound, just having effectively magnitude and time, um, or signal strength and time, or channel and strength, or that to my mind makes the idea of the mathematics simpler by reducing the size of the problem space. Okay, so we have our two tensors in effect, A and B. So let's print out what that looks like as a Numpy array, for example. Let's go print. I'll put this on a new line. Let's say I think it's S for complex types and strings. So we're probably going to use the array to string overload in effect on this. So we can do B. I think this is the format for doing insertion of strings without using the string format function. I'll try that. Has no float 32. Like I say, I don't know exactly what I'm doing. And the first time you play with this, it'll be a little bit the same. There we go. Okay, so we've got our shape, our 2x2, and it's of type float 32. All of that looks good. That makes some sense. I don't know what the cause of this is, whether it's the options that were installed with the CUDA driver or CUDNN or something. I'm not sure. Maybe it's something to do with this particular version of the NVIDIA drivers. It's kind of irritating, to be honest. All right, let's multiply these together. See, let's use TensorFlow.multiply. So we've got things here like square root. There we go. I don't know if that's matrix multiply or math multiply. I don't know what that's short for exactly. I would imagine it's for matrix multiplication. Let's pass it A and B. Makes sense. You need the two things to multiply together. And let's print out C and see what the result is compared to this Numpy array that we had the first time. Save, debug. There we go. For matrix multiplication of our two tensors, our two tuples, comes out with a shape like that. There's nothing that means that you would need to use a GPU to do this, but this is the kind of mathematical multiplication that, or mathematical operation that GPUs are particularly good at. Can do them in massively parallel senses. That's why GPUs are so good for this kind of task. They're much more specialized in the multiplications. And earlier I said, convolution, for example, the recursive multiplication. That's effectively this operation. If you're doing that to say colors or pixels, you can apply a filter over the top of an image, for example, and then use the matrix multiplication to apply that moving filter over an entire image. and moving that filter piece by piece over the filter kernel, which is larger than 1 pixel, over the image, 1 pixel to the right, and then doing the matrix multiplication, and then doing it again and again and again. It effectively cascades the multiplications into each other. Every time your, say, 3 pixels of kernel move 1 pixel at a time, you effectively multiply the same pixel three different values 3 different times as you move across it. So that massively recursive multiplication is one of the things that GPUs are particularly good for. And that's what they used for in 3D graphics, for example. It just is a happy byproduct for us that this massive performance for that pixel manipulation turns out to be useful for this kind of thing as well. So if we wanted to iterate through all of the dimensions in one of our tensors, for example, we could say for I in range, and so here we had shape 2. So if we take the first array position out of that, we could do a.shape 0. So that's that first dimension. That should give us the length in 1 dimension. And then we should be able to do for j in range, still in A, but this time we want to take the second dimension. Print, it's going to be A, and we want the ith and the jth component of the array, the tensor. And this time we're going to say, value. I know the only reason I want to do this in particular is that I want to be able to, to put a new line on the end of every one of them. So let's try that and run it. Now we should get a 2x2 list of our, there you go, of our values, 4 values. So that's how you iterate through both dimensions in the tensor. So we started off with 2, 1, 1, and 0.1. So 2, 1, 1, and 0.1. So this gives you an idea of how the mathematics works that underlies all of these things. Later on, we're going to want to multiply, do these matrix multiplications, add parts together, do things like that. Understanding, the very basics of the manipulation of these data types is a great place to start, because without that, you're not going to be able to understand the more complex ideas of things like the tensors, their activation strength, and things like that, which, like I say, I don't really understand either, but we're going to find all that stuff out together, hopefully. Either that, or I get bored with making these videos, or I run out of bandwidth to upload them. But yeah, stick with it, and hopefully we find out some interesting stuff.